Okay, well, thank you everybody. And Francesco, that was fantastic. I took the advice of the LOC to try to give you a little bit of history about Italian neuroscience. So my talk would be a little different. I'll tell you first about Angelo Mosso, what did he do for a few slides. And then I will discuss one experiment that will try to test the idea that the functional connectivity, the spontaneous activity patterns in the brain, are actually not just related to structural connectivity or neuronal synchronization, but are actually representing information states. So, Angelo Mosso was born in Turin in 1946. He graduated from medicine also in Turin, summa cum laude. Then he went to Lipsia to learn how to measure vascular fluctuation using different kinds of devices. He came back to Turin and eventually established as a professor of physiology the Institute of Physiology that became the best academic institution at that time to study the brain. Mosso was also kind of a Renaissance man. He was interested in archaeology. He's also set up a lab in the Alps to study the effects of hypoxia. That was in 1907. And eventually, he also apparently was also a bit of a rascal because he died of syphilis in 1910 from secondary syphilis. Now, he was of humble origin, and his father was a blacksmith. And he was able to learn how to use his hands and build devices. And in 2014, in the Accademia dei Lincei, which is the Italian National Academy of Science, this new manuscript of Mosso surfaced, and there was a nice paper by Sandrone and collaborator, and Daniela Perani, our co-chair, is on the paper. And in this paper is described very beautifully the first neuroimaging device that Mosso designed. This is a balance table, very precise balance in which the subject was on the table, and then at that point, with a lot of controls, the subject was asked to perform different kinds of cognitive operations, and depending on the tilt of the table, Mosso tried to determine whether increase in blood flow or increase in circulation due to cognitive function would eventually tilt the table towards the head. Now, this experiment was then replicated in London. Unfortunately, the results are mixed. We still don't know whether your brain changes its weight when you're performing cognitive functions. Now, I did a little bit of research in my own institution in Padova. Padova is an old university. It's been around for about 800 years. So we have an old institute, and we have a very damp and dark basement in which we have all the historical books. So I went digging out in the library, and I discovered this other book by Mosso, The Temperature of the Brain, La Temperatura del Cervello, in which now he's using thermometers, mercury thermometers, very precise, that he was actually to place into the brain of these people with open skull injuries. This is Luigi Cane, one of his patients. He was a worker. A brick kind of fell on his head, creating a fracture. He also had a CSF leak. And Mosso was able to insert the thermometer inside the parieto-occipital region of Luigi Cane and ask him to perform different kinds of calculation. In another experiment, he used something called a plethysmograph, which is basically a machine to measure pressure in void. And so he was able to apply, let's see if I can use here my mouse. Mouse doesn't work, but anyway, here on the right side, you see the cup. The cup was applied over the parieto-occipital region, and then the little cuff here indicated by N and M, that was applied on the foot. Vacuum was produced in both devices, and then Mosso was able to record curves of fluctuation of the pressure in the brain, on the surface of the brain. That's the tracing on the top. And then he was able to also measure fluctuation in the fluctuation of the blood vessel at the bottom. And what you can see in the top trace, you see this beautiful slow frequency fluctuation from the brain. And then at some point, he asked the subjects to perform a multiplication, 21 times 13. And now these workers start, as you can see, the fluctuation from the brain. There is an increase in volume, a slight increase in volume. And you also see that the amplitude of those fluctuations is increasing. At the point W, towards the end of the tracing, you see that the subject now is performing a response. the response was actually accurate, and you see even a greater fluctuation in the brain. Simultaneously, the peripheral blood vessel, this seems to shrink. There seems to have a decrease in volume, and you see also decrease in the fluctuation of the peripheral capillary. Probably the subject was very much stressed out, his noradrenaline went up, and that probably caused a vasoconstriction of his peripheral bed. Now, as you read the book, it is pretty clear that Mosso was concerned with some of the same issues that we're dealing with in neuroimaging. He knew that he was doing measurements from the brain using indirect means, which were very low signal to noise, not different from fMRI. He was also using multimodal measurements to try to get some grip on the sources of the variability. On the table, on the balance table, he had posts that was measuring actually head motion, and he was also had belts to measure respiratory artifacts. He also used modern task design, comparing rest to task, and also comparing parametric manipulation of cognition. One thing that I really like about Mosso's experiment is that he was actually to measure simultaneously both the brain and the body. I think this is really one of the next frontiers. We've been studying the brain as almost like a disembodied organ, the brain by itself, but we really need to understand how the brain and the body are connected. Now, one of the issues that I think is fundamental in neuroscience today, and the links the brain and the body, is the question, what is the function of brain energy? The brain weighs only 2% of the body weight, yet it consumes about 20% of the body energy, and we still don't have a clue what is all that body energy for. There have been a lot of calculation, theoretical and empirical calculation, trying to understand where that energy is going. We know that both in the cerebral cortex and in the cerebellar cortex, about 1/4 to 1/3 of the energy goes in maintaining the membranes, changing the mitochondria, basically kind of protein production, mitochondrial leak, and other non-neuronal function. However, 3/4 of the energy goes in neuronal signaling, of which action potential that are energetically very expensive consumes very little, maybe between 10 to 20%. And most of the energy goes in synaptic transmission, postsynaptic transmission, that is slight membrane oscillation at the postsynaptic side, whose function is at this point not very clear. At least in the cerebellum, Atwell and collaborators have done calculation, tried to compare different computational strategies in the cerebellum, and they've argued based on this metabolic calculation that the output of the cerebellum, the Purkinje cells, are actually using only 20% of the energy. When the cerebellum kicks in and is basically correcting or anticipating the motor response in the motor cortex, that is what that 20% is about. However, 80% of the energy in the cerebellum is in mapping all the possible input and output operations, all the possible repertoire of stimulus response mapping that the cerebellum can do is actually where the energy seems to be consumed. So at least in the cerebellum, we don't know in cortex, but at least in the cerebellum, the energy seems to be going to representing stimulus response or stimulus cognitive response mapping. And that leads us to the question of the resting state. So this is a movie of a brain, a rest. These are the fluctuations that we're measuring with fMRI. And these are some of the ideas that people have put forward over the last few years. One idea is that this functional fMRI fluctuation are reflecting synaptic homeostasis. In other words, is maintaining the synapses connected, and this explains why structural and functional connectivity are similar to each other, but particularly under conditions in which there is less cognition, for instance, sleep or coma. Another idea is that these fluctuations are reflecting communication through coherence, neural synchronization between regions that are activated during a task, and then through Hebbian plasticity, this activation, this correlation are then maintained in the resting state. A third hypothesis that what I'm going to test with my experiment is this idea that the brain is maintaining representation in the intrinsic activity. In other words, it's representing not only the communication between regions, but is actually representing information states that are important probably for biasing what we might be doing during cognitive tasks. So the hypothesis then that many people have proposed, and our group has also worked on this, is this bilateral relationship between task-driven activity, determined to some extent by genetics, development, and your own experience. So our brain, although very similar, is slightly different in every one of us. And this task-driven activity can then lead to fluctuation in the resting state. And in turn, this fluctuation in the resting state can be considered spatiotemporal priors for task-driven activity. What I'm concerned with, however, is the multivariate representation in every particular brain region and the changes between these regions in these multivariate patterns. This is what I'm looking at. Typically, regional or IC-based functional connectivity is considering a region as a unit, as a node. We talk about node and edges, but of course in any regions there are like hundreds or thousands of voxels. So we're going to test this idea in human visual cortex. Human visual cortex is a system in which you have a gradient of activity as shown by people like Nancy Wisher and Jim Axby. They're basically a gradient that represent different kinds of information: faces, bodies, tools, scenes. And one of the most interesting results of this line of work that has been going on now for 20 years or more is that there is a low dimensional structure in human visual cortex. There is basically a difference between the activity pattern for animate stimuli, faces, bodies, mammals, and non-animate stimuli like tools, chair, musical instruments, and scenes. And this very low dimensional structure, you can see it here in human IT cortex. So what we're interested in asking is, are natural visual stimuli represented in human IT cortex also during spontaneous activity? And in order to do this, we developed a data set of stimuli containing 10 different categories and multiple repetition of the same stimulus or different stimuli for each category. And first we scanned people with a block design to identify a region in human cortex. Then we scanned people with an event-related design to basically get a multivariate classification for each individual exemplar and then for a category as a whole. The experiment went like this. We first got resting state, so the subject did not know what they would be doing in the following of the experiment. This resting state was acquired for about 30 to an hour in different sessions. Then we obtained localizer scans to localize regions in human occipital cortex, and then we obtained event-related scans to basically get multivariate classification. So first we localize the region in extrastriate visual cortex, and we see the classic regions that everybody has been studying. EBA by the contrast of body versus objects, fusiform face area, face versus objects, and parahippocampal place area for scene versus objects. Of course, these are the canonical regions. In reality, we have multiple regions for each category. So we have 6 or 7 body regions, 3 or 4 face regions, we have about 9 to 10 scene regions. And so for improving the classification and simplify the computation, we put everything in a joint ROI. That is, we vectorize these regions and we call it a joint body ROI, face ROI, and scene ROI. Then we test the representational similarity, the kind of experiment that Jim Axby and others have done. And now we present multiple objects. For instance, here at the bottom, you see multiple multivariate responses for different kinds of scenes. We can then look at the representational similarity across all the stimuli, and you can see that in EBA, for instance, stimuli that are classified as mammals, body, and faces produce more similar responses in task evoke activity than other kinds of categories. We then take all the body regions, and we obtain a body joint ROI, in which we also get representational similarity maps. And now this is basically a map across all the body regions. The fourth step is taking this template of different categories or individual template, individual stimuli, and slide them along the resting state of the subjects before the experiment was performed. So here you see on the left side the multivariate template for the scene average template. And in the resting state, you see that curve that represents the similarity between the stimulus pattern and the resting state pattern frame by frame. And on some frame, you get, for instance, on the right, in the purple, a very good match between the stimulus and the resting distribution of activity. In other frames, for instance, in the green frame, you get no match. And in the blue frame, now you get a negative match. You get both transient, negative, and positive matches, and a lot of non-zero matches. So we can draw now a distribution of correlation values, and we're going to take the U90 value, the top 90% values, as our measure of basically match between the resting activity and the task activity. And at this point, what we can do, we can put all this distribution and compare the distribution with control stimuli. In this case, the control stimuli are the phase scramble phases. These are artificial stimuli that, according to the two-way reciprocal relationship between task and rest, should not be represented as commonly. And what you can see in the distribution, you see that the target category phases are actually wider, so that you have basically more matches for phases than artificial phases. And at the bottom, you see the U90 values, and you see that again in the resting state, you get a better similarity at rest for the categories that are related to phases and not similarity for the other categories. We repeat the comparison for body, and we get exactly the same results. And again for scenes, and we get again the same results. And now you can see that the scene similarity in the scene prefer ROI is actually the highest. So at this point, what I show you is that at rest, there are moments in time in which your resting state activity is resembling canonical pattern of task evoke activity within a region. Now the question that I would like to ask is whether this is actually co-occurring in time, so that we have phase state-like patterns in visual cortex as compared, say, to body-like patterns in visual cortex across multiple regions. And in order to do that, I'm plotting here the 6 different body regions in terms of their similarity between task and rest. And you see that although, of course, the average has a lower similarity value, there is quite a bit of variability, but all of them show kind of a peak at the level of the body category. And over here we see the scene regions, and again there is a little bit of variability, but all of them, they show a match at the moment in which scenes are presented. At this point, we're ready to look at the functional connectivity between these regions. So if we take 2 body regions as an example, and 2 scene regions as an example, and now we're taking the body pattern, and we're sliding the body pattern across the 2 body regions, you see at the bottom, the blue and the azure line, that those regions are showing correlated fluctuation in body template. If I go in the scene region, now I see that when I show a scene template, those regions will show fluctuated correlation in scene template, but not in the opposite one. And what you can see here is that these states are actually occurring independently. At this frequency, either you have a scene template in your brain or you have a body template in your brain. When you look at all the regions, and across all the different subjects, we get a nice, at the bottom, double dissociation. So when you use a body pattern, body ROI will show more similarity at rest. When you use a scene pattern, now scene regions will show a greater similarity at rest. Now what about the correlation with the functional connectivity? When we go and look at compare what we call pattern-based FC, which is basically reflecting this multivariate classification with ROI-based functional connectivity, we see in every subject a match between 0.7 and 0.85, suggesting that what we measure as functional connectivity is actually a combination of pattern states that are cycling through in time. So, to conclude, fluctuation of resting activity in visual cortex encode preferred stimulus patterns more frequently than artificial stimuli. This intrinsic pattern fluctuation respects the topographical selectivity of visual cortex and the categorical similarity. So, in FFA, face and body patterns are more likely to occur than scene patterns. Now, you might ask why we see a change in the variance and we don't see a change in the mean. We don't know why that is. But one explanation is that we're only testing 40 faces, 40 bodies, 40 scenes. We're not testing the millions of faces that you might get exposed to. But nonetheless, These results has also been shown in animal work. These are data from Amir and Greenwald, optical imaging in monkey cortex. They developed task classification for, I'm done, task classification for orientation stimuli, and now they slide the stimuli in the resting state, and you can see here that the mean also in their distribution is about 0, with peak, positive and negative peaks in primary visual cortex during spontaneous activity. Okay, so I'm done. Thank you very much, and I'd like to thank my collaborator, Do-Young Kim and Gordon Schulman, and the paper now is in review, and some of you reviewers, please be kind with this paper because we think it's very important. Thank you very much.
Thank you. Thank you, Maurizio.